I'll be discussing molecular orbital theory, which is one of the major approaches to chemical bonding. There are various postulates of molecular orbital theory. The first postulate states that the electrons present in a molecule are present in the various MOs. They come from the different atomic orbitals. So what that means is, in case of, for example, a molecule like H2, it is formed by the combination of one H and another H. So since there is one electron in each H atom, the H2 molecule has two electrons which will be accommodated in the molecular orbitals. The second point states that atomic orbitals of comparable energy and proper symmetry combine to form molecular orbitals. So two factors are important for a proper molecular orbital formation. The first being proper symmetry match and the second being proper energy match. The third point is that the number of molecular orbitals formed is equal to number of combining atomic orbitals. That is, when two atomic orbitals combine, two molecular orbitals are formed. So the number of orbitals is conserved. The fourth point states that bonding molecular orbitals have lower energy and hence greater stability than the corresponding anti-bonding molecular orbitals. These are the four basic postulates of the theory. Now moving on to some other aspects. If we, let's say, consider the formation of H2 molecule. So that is formed by the combination of one H atom with another H atom. So there are two types of combination. One is the difference and one is the sum. That is, each hydrogen atom is associated with a wave function. So if there are two atoms which are combining to form the molecule, there will be two associated wave functions, one for H1 and one for H2. They can combine either by getting added together or by getting subtracted. And there is another thing here which you need to know, that is the normalization factor. What is the normalization factor? The wave functions of molecular orbitals are normalized by multiplying by a normalization constant capital N, such that integration of n chi squared d tau is equal to 1. This is there in the notes that I have provided. What does this mean? This basically means that the probability of finding an electron somewhere outside the nucleus is unity. That is, outside the nucleus anywhere we will definitely find an electron. What is the value of this normalization constant? If the wave function is represented as chi, where chi is equal to a chi 1 plus b chi 2 and so on, then the normalization constant is equal to 1 by root over a square plus b square plus whatever other constants there are. So in case of the hydrogen molecule, since two atoms of hydrogen are combining, therefore the n is equal to 1 divided by root over 1 square plus 1 square, which is equal to 1 divided by root 2. So here I have shown the linear combination of atomic orbitals for hydrogen. See, HA is one atom and HB is another atom. They combine. If they combine as a difference, then this is the resultant molecular orbital, and if they combine as a sum, then this is the resultant molecular orbital. As you can see, they have been represented as sigma and sigma star. Sigma representing a sigma bonding orbital and sigma star because it is a sigma anti-bonding molecular orbital. As has been shown, the energy of sigma is lower than sigma star. Also, an easier way to remember this is, in case of the bonding MO, as in case of sigma, you can see that the electron density in this region between the two nuclei has increased. So this is stabilized. And in case of the anti-bonding MO, here there is no electron density. In fact, there is a nodal plane here. Nodal plane signifies a plane where there is no electron density. So what is the consequence of this? If there is a nodal plane, then these two nuclei are not shielded at all. That is, they are facing towards each other and they are going to repel each other more. So the system overall gets destabilized. This is also in keeping with the molecular orbital postulates, which states that the antibonding MO is of higher energy than the bonding MO. So this is the LCAO for dihydrogen. Now moving on to this lower figure, which is the relative energies of the MOs and atomic orbitals for H2. So this is the atomic orbital or 1s of one hydrogen atom. This is the atomic orbital of the other hydrogen atom, and the two combine to form two molecular orbitals. And in case of H2, there is one electron here, there is one electron here, and so there is a total of 2 electrons, and in the molecular orbital they get filled like this. In case of, let's say, helium, if we have He2, then in that case this will have 2 electrons, this will have 2 electrons, and the total net number of electrons will be 4. So in case of He2, there will be 2 electrons here and 2 electrons here. Anyway, so coming back to H2, what can we find out from this model? We can find the bond order. Bond order is equal to the number of bonding electrons minus number of antibonding electrons divided by 2. In case of the H2 molecule, number of bonding electrons is 2. So 2 minus 0 divided by 2, which is equal to 1. So the bond order of H2 is 1. From this we can say that the number of bonds between the two hydrogen atoms is 1. Also, what else can we take away from the bond order value? Firstly, from the bond order value we can judge whether the molecule is stable or not. If we have a 0 bond order, it signifies that that particular molecule is unstable and might not exist. Also, the bond order is inversely proportional to bond length. That is, the higher the bond order, the shorter is the bond length. So these are the basics or the introduction to molecular orbital theory. Later we will go into specific MO diagrams for various homonuclear diatomic systems and heteronuclear diatomic systems.